Yeah, thank you, Koei. Yeah, thanks everybody for a tremendous welcome yesterday with so much good food, which I really enjoyed. And yeah, maybe I mentioned yesterday I was here 8 years ago, and I think your group was about 5 to 10 people. And looking at the room here, it's gone pretty well, I guess. 2 groups. Yeah. So it's a real pleasure to be back. So maybe coming to the talk, it's a bit different from a normal seminar talk. So I decided to do things. One is a general introduction on just what we do and on our group, such that you have an impression on where Kohei Ohashi was when he stayed with us. And then the second part is a bit more of a progress report, which is a bit more detailed, but on the NV work, which was partially in collaboration and shows our side of things. So this is an image of Zurich as you travel up to the main campus, which is located on a hill. And I think when Kohei was staying, he was a bit lower, but roughly with that perspective from his dormitory. So if anybody else of you is ever in Zurich, feel free to come and visit. So this is during the summer. When Kohei visited, it was more a bit like this, which it actually is right now. It's about 10 degrees and a lot of fog, so it's a real pleasure to be here back in the summer. So actually it's a scenic view, and when I was a PhD, I was taking between 50 and 100 images over a year and made a calendar out of it with all types of views. Okay, so then to our group, so I joined ETH 2 years ago. Before that, I was for 2 years as an assistant professor at MIT. So this is how my group started in 2009, 2010 with 4 people plus 3 people plus an undergrad. So this is how it looked like when Kohei came, and I think he's also on his here. So it was a really snowy winter, which we had to hurry out and take a picture and hurry back in. And now my group is that's back in the summer. We are now about 15 people. So we've also grown quite a lot. Actually, I hope we don't grow too much anymore because it goes very quick. And we have, just for the records, we have 5 people, 4 postdocs and PhD working on NV centers, and about 7 on this so-called MRFM, which is a force microscopy technique. I'm mostly going to focus on the NV part because I know this is where we have the closest connection. Okay, so what do we do in our lab? So the overarching goal is to do nanoscale MRI using new techniques, new types of sensors. And this is just a demo image of what you would think of nanoscale MRI. So this is the MRI you get in a hospital. You have a head, and the resolution is on the order of 0.1 millimeter in a voxel size. You can improve it making microcoils, but then your head won't fit in anymore, to maybe 10 or 3 microns. That's about the best. So what we would like to do is to take the same 3D MRI images, maybe with spectroscopic NMR resolution, meaning you can differentiate elements on large biocomplexes. So this is an example where you have virus particles. They don't look too fancy. These are long rods of virus particles, and you can see a cross-section through them. They're called tobacco mosaic virus particles. And they sit on top of a gold surface. And what we see that gold has a small layer of hydrocarbons and water on it. And you also see in this MRI that there's a layer of hydrocarbons, and on the top of that you see virus particles. So if you would want to improve on that, what we want to do in our lab is to take a higher resolution image of the virus itself, such that we can start seeing individual proteins in the virus. Eventually maybe extending to atomic resolution, meaning you see single spins and you know where the location is. But as a tool for other areas of science, structural biology or chemistry, where you can analytically analyze a surface. So this is the overall goal, but this is what we like to get images. What we spend 95% in the lab is improving our instrumentation, and we're working on 2 different methods. So this is the topic of more everyday research we have in the lab. So this is the goal here, to develop a nano MRI technique that has a much higher, like 1,000,000 times higher resolution. The tools we use for that is, on one hand, is force microscopy. So we take these small nanomechanical beams or micromechanical beams. We attach a sample or a magnet to the end, and then we measure a magnetic force between spins and the magnetic tip. And this technique is also called MRFM, or magnetic resonance force microscopy. So this I'm not going to talk about today. The other part is that we use for different types of sensors, and in this case a single NV center in diamond with the same purpose as a small magnetic field sensor that can pick up the dipole fields from nuclear spins and do a similar kind of 1D, 2D, maybe 3D mapping of positions of nuclei. And then the last part which comes into it quite often is spin physics. So what does change if you go from 10 to the 20 spins in NMR to 10,000 spins in this virus to a single spin? So this is the overall topics that go into the lab. Okay, so staying with this one here, actually I grew up as an NMR spectroscopy person and also force microscopy. So what brought me to this field of NV centers? It was this kind of proposal that you could think of not using a magnetic tip, but you could use a single spin in diamond or another material, and then this spin can couple like a dipole to other spins. And if you're able to read out the resonance of this spin very precisely, you can precisely determine what the distance is and what the type of nuclei is that is close by. So this is a standard NMR or EPR technique. You measure a dipolar coupling. And this goes back to a proposal by us in 2008. A little time later, there were also two proposals by Harvard and Stuttgart, but it was kind of the initiating that you could use NV centers not for quantum information, but for sensing. All right, so what I'm going to do now is give you a little bit an introduction on the NV center from my perspective. I know many of you guys know the NV center, but I'm just going to tell it from how it looks from our side. So maybe for the ones less familiar, you will have another opportunity to view that technique. So the NV center is you take a diamond, ideally a pink diamond. I just recently heard there was a new pink diamond on sale, I think at an auction in Geneva, which is, I don't know, 100 carats or more, and it costs 60 million. So obviously not the type of diamond we're going to use in our experiments. But the pink color comes from defects, and in particular in this case this NV defect. So you have the diamond lattice here, and then you have a nitrogen atom which replaces the carbon, and next to it you have a vacancy, so a missing carbon. So in some sense it's a molecule. One atom is a nitrogen, the other one is a carbon that is not there. But it behaves like a molecule, and it's not in vacuum, but it's embedded in a diamond matrix. So we can do all the molecular spectroscopy techniques on this molecule that one would do on molecules in the gas phase. And gas phase spectroscopy is very well developed. Okay, so we don't use these 60 million, 100 or 1,000 carat diamonds. So what we use is either nanodiamonds, and the smallest you can find are maybe 4 to 5 nanometers, still having an NV center. So this is a TEM of so-called detonation nanodiamonds. So they're made by putting TNT and another explosive in a closed vessel, and then you ignite it, and from the high pressure, high temperature, you get synthesis of nanodiamonds. This was invented by the Russians in the 70s, I learned. But it was all closed in behind the Soviet Union iron wall, and it made it in the 80s or 90s to the Western world. So we've started using those, but we don't use them too much anymore. We started focusing on so-called single crystal diamond, which we mostly get from this company Element 6, because they have the highest quality. So what you see here is about a 3 by 3 millimeter crystal. It might be even a bit larger, which is pure single crystalline diamond with very low nitrogen concentration. So we started also shaping this diamond into geometries that we like better. One is we started to making pillars. So etching into the diamond, the pillars have two advantages. First, they can act as photonic light guiding elements, so we might get a better photon emission property if there is one of those NV centers right in here somewhere. We can also make very sharp tips, which might be very useful for AFM scanning, as we eventually come to. We also started making cantilevers. So what you see here is a diamond membrane, and you see some, well, you don't see them too well, some tiny bars sticking out, which are flexible cantilevers that are also used in AFM. So shaping single crystal diamond into a structure which is more useful or more amenable to this scanning microscopy. Okay, so this is the type of diamond we use. Most of this diamond has natural NV centers occurring. So in order to study an NV center, we use a setup that basically 90% of the community uses, which is a confocal microscope operated at room temperature. It's all home built, but it uses all the classical elements of a confocal microscope. So you have a laser here, which we use a 532 nanometer green light because it's very available. We have a so-called acousto-optic modulator to turn on and off the laser for pulsed experiments on 10 to 100 nanosecond time scale. And then we have two so-called pinholes, so we focus the light through a tiny hole, which gives so-called confocal resolution, meaning the spot in the diamond, which is then going to sit here, is focused, the green light is focused in one spot, and the red light is detected from the same volume element, and this helps suppressing the background a lot. So we have a second pinhole here in the detection pass. So this goes then through a mirror, which is semi-transparent, so it passes red, but it doesn't allow the green light to go through. It goes through a high NA objective and then onto a stage where our sample sits. So this stage can scan in XYZ. Sometimes we also scan the beam. In some setups that we have in total 4 setups. 2 have an AFM attached to it. So we have a cantilever that we can scan around. 2 are simple optical setups without this AFM cantilever, just for studying properties of NV centers or testing sensing protocols. And then we have microwaves connected that come in through a coaxial cable and then to a strip line, which we evaporate by gold on a glass slide usually. Or we take a tiny wire that we turn over the diamond. So this is an image. If you take one of those diamonds from the previous slide, from this element 6, you zoom in and you take a fluorescent image, and all the bright spots you see here are individual NV centers somewhere deeper in the diamond. And this is natural occurring NV centers. We have nothing done to enhance them or make them purposely. Okay, so just one slide or 2 slides about how the physics works of the NV center. So we see they absorb green photons and they emit red photons, and you can get a bit more specific. So by drawing a band structure and an energy level diagram. So diamond is an insulator, so you have this 5.5 EV or about 220 nanometer light band gap, so it's an insulator. And then all defects, not all, but many of them form discrete levels within diamonds. So for the NV center, it's 2 main electronic levels, which is a ground state and an excited state. So you can excite the electron from here to here. If you excite really well or use some other tricks, you can sometimes also excite it out of the diamond. So then it ionizes, so it's not the NV minus, which we usually have, but an NV neutral. For the NV center, it's a spin 1 defect, so it has a triplet ground state. So it has not only an electronic level, but if you look very finely in here, so this is exaggerated, we have 3 levels, which is an MS equals 0, so a spin equals 0, and a spin equal plus minus 1. And the plus minus 1 are degenerate, the 0 is not degenerate, which comes from the symmetry of the NV center. So we can excite this using green light, and then we have red photons that are emitted in 70, 80, 90% of the case. And there is a lifetime of roughly 15 nanoseconds. And the emission is, so we here have of course one wavelength. The emission is very broad, so we have a range of wavelengths. So there is one important feature. The NV center has not only one way to decay from here down, so route 1, but you also have a route 2. So the NV center can relax, or the energy from the electron can also be spent by going to a third, okay, it's a double, but to a third singlet state, which is much longer lived, about 300 nanoseconds. And this alternative path also leads down to the ground state. So we have 2 choices, the direct route number 1, which gives you a red photon, and the route number 2, which doesn't give you a red photon. So now the key thing to see is that these routes are taken dependent on whether you're in 0 or whether you're in 1. So if you're in 0, the green light is going to excite you to 0, spin is not affected. In most of the cases from the 0, you fall back again to the 0. So it's spin preserving. If you go from the 1, you have the same, you go to the plus minus 1, you come back to the 1. But if you're in this 1, you have a decent chance, let's say 20, 30, 40%, that you take the detour number 2. So as you are in the 1 state, you have a long wait time here. And then, because it's a singlet state, the spin changes, it goes back to 0. So you have two features. One is if you're in the plus minus 1, you often take a detour, so you have less photons on a long time average. So it's less bright. The other feature you have, if you ever take the detour, you're always going to end up in 0, so you pump your system into the 0 state. So from a quantum perspective, this means you have a way to read out your spin state. Many photons are bright, means the 0 state. Few photons are red, means the 1 state. And you have a way to initialize it. By shining green light, it will automatically go back to the 0 state. So the 0 state is usually called the bright state, and the plus minus 1 the dark state. The difference is it's not really dark. So if you have 100%, or let's say 100,000 photons per second measured here, you might have 70,000 here. So it's not such a large difference. Okay, so this is how the photophysics works. So now we can focus on this transition here and start doing so-called optically detected magnetic resonance. So we can take a microwave field and start changing the spin in between here. So it turns out the energy gap is roughly 2.9 gigahertz in frequency units. This is much, much smaller than the 1.94 eV. So you can measure this by shining green light on your NV centers, collecting photons all the time, and at the same time applying microwaves and changing your frequency very slowly as a function of time. So if you change your frequency slowly, then as you reach the resonance, suddenly the NV center, which is now mostly in 0 because you're always repumping, has a chance to go up to the 1, so the fluorescence drops. So what we see in the spectrum is that as soon as the microwaves excite the transition, there is a sizable fraction of that the NV center is in the plus minus 1, and your intensity drops by, okay, here it's about 27%, not 30%. But this is your hallmark of that you have an NV center. And in our lab, it's the way we usually discriminate an NV center from any other type of fluorescence. If we see this signature, we know it is an NV center. Okay, so this is just a way you can perform magnetic resonance. So now how can you do sensing? If you apply a magnetic field, then the magnetic field will affect those levels here through the so-called Simon effect. So the field will not affect the 0 level, but it will raise the energy of the minus 1 or the plus 1, and it will lower the energy of the minus 1. So if you apply a magnetic field, then these lines will move apart, and if you look at the spectrum, you're going to have two lines. You have a transition from 0 to minus 1, which is now a bit lower in frequency, and 1 to plus 1, which is now higher in frequency. So what the nice feature is that there's a very strict relation between the frequency and the field you apply, which is given by the so-called gyromagnetic ratio. So it tells you that if you apply a 1 Tesla field, the plus line will move up by 28 gigahertz. The minus 1 line will shift down by 28 gigahertz. So 1 Tesla is a lot of field. You would shift the lines tremendously. So usually we apply 0 to up to 200 millitesla field. So here you see one example where the frequency difference is roughly 250 megahertz. We can divide this by this factor here, and we get the magnetic field. So we have straight from the spectrum a measurement of the magnetic field at the position of the NV center. And this is the basic feature which all this magnetic sensing and magnetometry is building on. Okay, so this is the very generic way, and you see that the sensitivity is roughly given by how wide your line is. If your line is narrower, it's easier to see a small shift in the line. And the sensitivity here might be on the order of a bit less than a millitesla, but fortunately there are ways with pulsed magnetic resonance to get much better, and I'm going to come to that in a second. So this is the introduction of how you do magnetic sensing. So let me now move on to what we specifically work on to make this a scanning magnetometer that might be useful for nanoscale MRI. So this is the basic sketch from the beginning. So the idea would be to take a diamond tip of the ones I showed you before to purposely create an NV center at the very apex here, and then scan this tip over a surface which may have one surface spin, maybe others, and then you can detect the magnetic field produced by the surface spin as a shift from your NV center. So this is the basic idea, and the ideal world we can look a bit more closely how this is in reality. Unfortunately, reality is not as nice as our sketch here. So if you work a little bit, you see that your tip is usually not going to be this nice round shape here, but it's very jagged. It's not very clean. It has adsorbates, it has other spins around, it has charges on the surface. Then you will realize that the distance here needed is probably going to be less than 10 nanometers. So you need your NV center very, very close to the surface here. And you also need to be able to approach very close. And then you will realize you not only have your spin that you like here, but also a lot of other spins around. So if you put this into challenges or questions, then the question number 1 is, what happens if you move your NV center here closer than 10 nanometer? Or very close to the surface of diamond. Will the NV survive? Is it stable at all? Or what is going to happen? How do you get it there? So the second question is, how do we distinguish this one that we want to measure from all the other spins around here or from the ones on the surface? Because all of them create magnetic fields, but how do you know that the magnetic field you measure is coming from here or not from here? And then the last question is, how do we get the NV center in this position here? How do we make a tip? And how can we start doing this just technically? How can we do scanning with all the components of optics, microwaves, a cantilever, all in one spot? So let me start with the first one. So actually this is the outline. I'm already over the first point and address the 3 questions by looking at the properties of very shallow NV centers, something we've done in collaboration with Kohei and some people in the groups here. Then I'll explain in some of the more advanced magnetic resonance protocols that we can do spectroscopy with an NV center. So how will we single out individual nuclear spins or a bunch of nuclear spins? And then I'm going to show you some first scanning experiments where we integrated everything in a scanning apparatus. Okay, so the experiments that we would like to do looks like this. Let's take a surface of diamond and have an NV center and just slowly move it towards the surface and see what happens. So if you move your NV center to the very top of the surface, it will at some point chemically not be stable anymore. The nitrogen might go away. But there is other things that can happen. The NV center has, for example, a minus charge. And it may be that as you approach the surface, the NV ionizes, and that has actually been seen. You don't know whether your spin that you have in here is actually stable as you get close to the surface. So what we want to know is what's the minimum distance that an NV center is just functional, that we can see it in the optics. What is the minimum distance where T2 or spin lifetimes are not compromised? So we set out with a sample made by so-called ion implantation. So this is a sample you see here on the left. So one way to create NV centers at a certain distance is to shoot nitrogen ions into the surface of diamond. And by tuning the energy, you can know where your nitrogen roughly ends up, not exactly. It has some disadvantages. If you shoot nitrogen in, it's like a bullet. It creates some vacancies around, so it disrupts the diamond a little bit. But at least you can create them very close to the surface. So we use this energy here, about 1.2 keV, sometimes higher, which creates defects on the order of 2 to 3 nanometers. More recently, and in collaboration with you guys here, we've looked at a much more sophisticated way to create NV centers at the very surface, which is by growing diamond and purposely doping it. So the advantage is that we can very finely tune the composition of the top surface, and we can also not have vacancies or have less damage from the implantation that we have on the left side. So this is a sample we've studied in collaboration with you, which is the same substrate, but then it has a layer of C12 diamond, and I'm going to mention why C12 is better. And then on top it has 5 nanometers, which is purposely doped with nitrogen, and some of them are NV centers. So let me start with the first sample on the left side. So how do we do the implantation? We don't do it ourselves. It's done in collaboration. We take a piece of this diamond. In this case, we created a whole map of implantation spots. So what you see is a fluorescent image. The size is 2 millimeters here and 1 millimeter. And we've raster implanted the entire surface with varying energies. So high energy here, low energy there, and then we also can vary the dose, so how many NV centers, how much nitrogen is going into it. And what you can see here nicely is as you have a high energy, you have more NV centers formed. As you lower the energy to, in this case, 0.4 keV, you have less NV centers formed. And also if you have a higher dose, it works better. You can do simulations to find out what energy corresponds to what depth. This is approximate because it's only a simulation and there is a distribution. Okay, maybe I should add that if you zoom up here in one of those spots, so these are not NV centers, this is a huge area. One spot is about 25 microns. If you zoom in, you can actually see individual NV centers. So there is a huge density in the spot itself, but if you look at the perimeter, you can see individual NV center by zooming into that image. So this is the conversion I mentioned. So you can do a simulation and find a mean depth. So on average, what's the depth if you shoot the nitrogen ion? The lowest is here 1.1 nanometer. The deepest is 7.8. We don't know that the NV centers we see are actually at this depth. For example, if you're up here, you can argue you only see the NV centers which are deep enough, and all the higher ones you don't see anymore. So then we can analyze the emission from those NV centers, and one thing is we can find out how many are our NV centers with a minus charge, which is what everybody means when he says NV centers. There's also an NV0 or a neutral charge state. There's even an NV plus. So through optical spectroscopy, you can find out what the concentration or fraction of NV centers is. So here we see that as we're deep, we basically have a constant NV concentration. As we go less and less deep, we see the concentrations go down. We also see that the ratio starts to be more in favor of the NV0. So as we get close to the surface, there are less NV centers, and the ones that are there are not in the charge state that we like. So talking in terms of stability, we see chemically less NV centers are formed. We see electronically the NV centers are losing the minus electron charge state. We have also looked at the spin properties here using a very simple measurement of this resonance line, which we call the ODMR line. So this is now a bit higher resolution, but what you see here is this optically detected magnetic resonance with the highest resolution we could achieve. And we can fit the line here and find it's about 2.2 megahertz, measured at this 2.9 gigahertz. We can do this as a function of energy. So you see this one here circled here was at 5 keV. If you go up, nothing happens until you hit about 1 keV or about this 2 to 3 nanometers. You start your line getting broader, and if you go less and less deep to the lowest depth, which would be a mean depth of 1.1 nanometer, your line is quite broad. So meaning as you get to the surface, there is more magnetic noise, your line starts to get broader, and this is a line width in a spectrum. If you would convert it to T2, it's a T2 star, or an inverse T2 star. So meaning your coherence times get worse. You can relate this to a model where you would have your NV center spin here, and you have a lot of spins at the interface. And then as a function of depth, we can calculate roughly what your magnetic field should be. And I'm going to do this in more detail on the next sample. So one thing we don't know is what are these magnetic defects on the surface, and here just a list, and I'm going to come back to that. It could be that these are dangling bonds, so the diamond has some unsaturated bonds which are paramagnetic, and this paramagnetism creates magnetic noise. You could have adsorbed oxygen molecules because oxygen as a molecule is paramagnetic. One proposition was also that there is charges moving around, and a moving charge will also create an Ørsted magnetic field. We don't know what it is, but we start to be able to narrow down what it could be. Okay, so this was our first study, and this is where I started talking to Kohei when we met at the conference, and we had this on a poster. And I think, remembering you mentioned that, oh, those guys can do this with implantation. I think we can do it with our growth. Mm-hmm. We can contribute a lot using isotopic and real doped growth. So we've repeated that with the second sample you've seen to do this more carefully. So I'm switching now to the second sample that we measured with Kohei, which was grown here and at AIST, and we started doing a more careful analysis. And one is, what is the influence if you change the surface chemistry of diamond on the NV centers? And as we received the sample, if you grow diamond, it has a so-called hydrogen termination, so the top carbon atoms are connected to hydrogen. And it's known that hydrogen doesn't really help stabilizing the NV center because it attracts negative charge, so the NV center ionizes more easily. Because there was heavy doping here, we still have a few NV centers, but you see if you change to so-called oxygen termination, oxygen is more negative, so it allows the NV to be more stable in a negative state. We had an increase in the density of NV centers by not too much, but a factor of 1.5. We finally fluorine terminated it, and we had another increase by a factor of 2 to 3. So it seems like that oxygen, and especially fluorine, help stabilizing NV centers at the very surface. So this is a small step towards well-behaved NV centers, even closer to the surface. Some funny thing we noticed, NV center is always promoted as a unconditionally stable. It never bleaches. It doesn't blink like other fluorescent molecules. For fluorine termination, many of our NV centers actually started bleaching, and it's currently not known what the mechanism is. But it seems like that surface chemistry has a very fine role in what the properties of your NV center is very, very close to the surface. The other thing we did, and that was mainly after Kohei left, which is maybe more the progress report part, we started analyzing the T1, T2, and also so-called T1 row, which I'm going to explain you in a minute, relaxation times to find out more what is the density of these surface magnetic states, what's their correlation time, what is their magnetic property. So first of all, what we can do is we can make up a model, and what we think that happens with diamond, why are our lines getting broader, is that we have our NV center here, we have paramagnetic states on the surface, and these paramagnetic states, they create a dipole field. And what we see with the NV center is a cumulative magnetic field from all the dipoles, the electronic dipoles on the surface. These dipoles are not stationary, they're moving constantly, so we don't see a static field, but a fluctuating field. So we can derive a mathematical expression by integrating over all those dipoles and get an RMS magnetic field as a function of the distance to the NV center. And this formula looks like this. So you have to go through some math, and there is gyromagnetic ratios and mu naughts involved. But what you end up with is a number of 2.85 millitesla if you have a density of 1 spin per nanometer area at the distance of 1 nanometer. So it's multiplied by the density. It depends on the 4th power of distance. So if you move away from the surface, this magnetic noise very rapidly decays away. But we have a relation that if we can measure this one here, and we have a knowledge of depth, which we have roughly with this tailored sample with 5 nanometer surface, we can find out roughly what the density is. So what we're going to do next is trying to find an expression or find an experimental way to measure this RMS magnetic field. So what we want to get is reform this expression, find the density, by measuring the RMS magnetic field having a known depth, which is about 5 nanometer for the lowest NV centers, and we can divide it by the constant that we get from the surface spins. So how do we get this RMS magnetic field? And there it gets a little bit more involved, but I'm going to walk you through the steps to do that. How can we measure an RMS magnetic field? So we can measure it through the so-called spectral density. So these magnetic paramagnetic centers here, they're flipping constantly. They have a T1 time, they might have a T2 time, so it's a fluctuating field. If it's stochastically fluctuating, you have a so-called Lorentzian spectral density, which has this mathematical expression. So it has your magnetic noise is a function of frequency. It has a knee frequency, which is given by a correlation time, and it has a magnitude, which is the RMS value that we are interested in. This is also plotted here. So if you plot this function, it looks like this. At low frequency, your noise is constant. As you move to higher frequency and you move above your knee frequency, or 1 over your correlation time, then your magnetic noise starts going down. And this correlation time could, for example, be the T1 time of the spins on the surface. So what we would like to do is to find out what this function is here, this spectral density. Unfortunately, in NMR, there is a very well-defined way of extracting exactly this quantity, this spectral density, as a function of frequency. So what we've done in these experiments, by taking extra data, but also analyzing the data that Kohei has taken when he was with us, we've been measuring at 2 points in this spectrum, at a frequency omega 1, which is going to be the Rabi frequency, at omega 0, which is going to be the Larmor frequency, so this is about 10 megahertz and 3 gigahertz. We've measured this precise number here. And then, because 2 quantities are enough to fit the 2 unknowns, the RMS and the correlation time, we were able to extract the spectral density, a correlation time, and an RMS magnetic field. So the 2 measurements we've done is, first it's a T1 measurement. So the way this is done is in a pulsed way. So we excite the NV, we pump it to the 0 state, then we have a long delay time, which can be up to 10 milliseconds, and then we read out our spin state. As a function of time, so we do this for different delay times tau, we record this curve here. So if we pump, we're in the 0 state, it's bright, we have many photons, so we start at the high photon level. As time evolves, the spin naturally can flip because it's in the dark, it has a T1 time, which is a few milliseconds in a bulk typically. So as a function of time, this T1 time is going down. And we can fit this, and in this case it was an NV center very close to the surface, so the T1 time was reduced, and it was about 260 microseconds. So this gives us a measure at this point here. So we also need a point measured at a lower frequency, and for this we use the so-called T1 row measurement, which is kind of similar. So we pump our spin into the 0 state, and now we use a well-known sequence, which is a 90-degree pulse, a Rabi field which is constantly on, and another 90-degree pulse to convert it back. So what this does, it doesn't probe the relaxation, a T1 relaxation, but it probes the relaxation as your Rabi frequency is on, and it gives you a value of the spectral density at the Rabi frequency, which is given by the magnitude of this field here. So the curve we get is very similar. As a function of time, we get a signal magnitude which initially is high and it decays to a low value. And we can fit it, and in this case it was about 70 microseconds. So it's shorter, and this is to be expected. If you have more magnetic noise, your relaxation time is shorter, meaning at this point you would expect a short relaxation time, your relaxation time gets longer and longer as you move up. So it means that the 2 points we've measured are actually here and here, and not maybe here and here. So let me move on to the measurement. So this was one measurement here for one NV center. We've done about 10 to 15 NV centers for different terminations. So this is the fit you get first for the correlation time, measured for 13 NV centers with 3 terminations and also with an implanted sample. And what you see is this correlation time is actually very constant among all the samples. So it appears that these mechanisms, these surface spins, are all very short-lived, and they're all very similar, independent of surface chemistry and even of sample type. You see the scale here, it's about 280 picoseconds, and there is a very little variation. So it's a very, very fast flipping of spins on the surface. We can also extract the density based on these 5 nanometers, and we see that it varies between 0.01 per nanometer square. So this will be 1 spin every 10 nanometer on the surface, up to 0.1, so there will be 1 spin on a 3 by 3 nanometer area. So here there is some variation, but it's still almost within error. It looks like the fluorine was the nicest we could get. But the main conclusion is there is very little dependence on surface chemistry on sample type. So it's likely that this behavior comes from something which is maybe in the top layer of diamond rather than on the surface itself. We can also, knowing that the deep NVs are about 5 nanometers, we can scale the T1, according to the T1 values, we can place NV centers at, assign a distance to NV centers, and if you do that, we can bin them in roughly the distance they are from the surface. So if we assume that the deepest NV centers are at 5 nanometers by design of the sample, and we look at the T1 values we get, we can roughly place them according to depth. And here you would find that NV centers are mostly between 2 and 5 nanometers. Nothing is below 2 nanometers. And this is actually in very good agreement with other measurements from other groups and also nanodiamonds. So the smallest functional nanodiamonds are about 4 nanometers, meaning the best NV center right in the middle is 2 nanometers from one surface. So these 2 nanometers seem to be a threshold below which nobody having really proven that there isn't a stable NV center. It also means if we have an NV center about 2 or 3 nanometers from the surface, and we look at this density with one defect on a 10 by 10 nanometer area, that a single spin is very often responsible for the decay we see, the reduction in T1 and T1 rho we see as we come to the surface. So it's one spin is enough to enhance the relaxation. Okay, so maybe the last point, why not use T2? So T2 is very famous as decoherence time of spins, and in this case I believe it's actually not the best quantity to use. So I've shown you that we can measure T1 and it gives you our point here. We can use T1 rho, it gives you a point up here. If you do a T2 measurement, it's equivalent to measuring at even lower frequency. So we measure a point somewhere down here. Now it turns out as you go to lower and lower frequency, there is more and more 1 over F noise, which may come from nitrogen in the sample from other sources. So we found T2 to vary a lot and be not correlated with T1. So to prove this, we can plot T1 rho, so what we did before, as a function of T1. So we can measure T1 values from about 0.4, 0.3 milliseconds. The longest one we've measured were almost 10 milliseconds for fluorine. And we can plot them against T1 rho. So we see the ones with a long T1 are also the ones with a very long T1 rho. If you have a short T1, we have a short T1 rho. And this makes sense because it's you're just moving this curve up and down. If you're close to the surface, it's expected that both correlation times go down. So if this were true, then in T2 would also be set by surface spins, then it would also need to scale with T1. So you move close to the surface, T1 goes down, T1 rho goes down, T2 goes down. So if you plot T2 here, you see there's actually almost no correlation. If you have a long T1, then your T2 can be very similar to the T you get as you're at a very short T1. So if we accept that T1 is set by the distance to the surface, and this seems to make sense because T1 rho also agrees, T2 is very different. So in this sample, I suspect that there is a high nitrogen concentration, that T2 is dominated by nitrogen donors. I can't prove it, but this is our picture. But it seems like measuring T1 rho, which brings you up to quite a high frequency of 10 megahertz, is much more stable than T2. And this is also important for magnetometry. If you want to do a very sensitive magnetometry, you like to operate somewhere up here where you have very little background noise, very long T1 times, rather than somewhere down here where your times are short. Okay, so this was maybe the continuation of the analysis we did on your sample. The last thing we're trying around now, but I don't have data, is to measure this T1 time or also this correlation time as a function of temperature. Because if your surface spins are fluctuating, they have a T1, so we want to find out what this T1 is caused by. If you change temperature, it can either stay constant, meaning it's mostly flip-flopped between spins and it's a spin diffusion process. If it changes its temperature, it's phonon activated, and we can say, okay, the fast fluctuation comes from phonons that couple very efficiently at the surface. So this is the last measurement which is ongoing right now. Okay, so this was some extensive update on very shallow NV centers. So let me move on to maybe the shorter points on more applied. We want to do magnetometry. How can we single out specific nuclear spin signals, and then finally the scanning experiments. So I've shown, this is the overview. if you want to do NMR, so taking a step back and looking at it a broader perspective again, if you want to do NMR or detect a signal from a single electron or a single nuclear spin, how good do we have to get? So what you can do is you can plot the dipole field in units of Tesla as a function of distance you're away from the NV center or from this spin. So what you see for an electron at about 32 nanometer, you generate roughly 100 nanotesla, and this 100 nanotesla is a good estimate of what you can do with a good experiment, but not being really pushing it to the very limit. If you look at a single proton spin, the equivalent distance is about 4 nanometer. So we have to be very close. So one thing is, how do we get that close? How do we achieve this 100 nanotesla and not the 1 millitesla from the early slides? And then the other is, how do we single out a single electron or a single proton? And for the nuclear spins, the answer is magnetic resonance. So proton spins, they have an orientation, they flip with T1, but they also have a precessional component, they have a Larmor frequency. So if you have a proton in a 1 Tesla field, it's about 40 megahertz. In a 100 millitesla field, it's about 4 megahertz. So what we ideally would like to have is a scheme not to detect a DC magnetic field, but an AC magnetic field, which is precisely tuned to the precessional frequency of the proton, or also, let's say, carbon-13. Okay, so for that we have to go to pulsed experiments. I'm going to just show you one as a starter. I've shown you how you can measure the shift of a line and estimate the magnetic field. We can also do this in this T1 type pump probe experiment. So this is a typical Ramsey experiment. You pump your spin into the zero state, you apply a pi pulse, this creates a coherence. Your spin coherently precesses, if you look at it as in a vector in the plane, and after a certain time tau, you convert it back to either 0 or 1. And if you plot this as a function of time, so we do many experiments with increasing times tau, you see these oscillations between the 0 and the 1 state. And the nice thing is that from this oscillation period, we can exactly fit a frequency. This frequency is directly related to a magnetic field. So in this case, by fitting this frequency, we find out that the magnetic field is 4.533 millitesla. And just to show you how sensitive it is, we can change the field very slightly by 5 millitesla, and you get a new curve, which is actually, it's not 5 millitesla, it's 9 millitesla higher. And you see that the frequency here already changes quite an amount. So we could go much finer and still be able to see the different frequencies. So this shows you how sensitive the scheme actually is at measuring magnetic fields. And these are absolute magnetic fields, not relative. Okay, this is all DC. How do you move to AC? There we can dig more into the NMR literature and look at different protocols, and we've used two. One we've been using is spin echoes. So a spin echo is the same as you have here, and you insert a pi pulse. So the precession of one period is cancelled out by the second one. We actually don't use one pi pulse, but many of them. So we do an echo with many pi pulses. And then a thing you can do is you will realize this echo, it refocuses all of your interactions. You get very long T2 times. But there is one specific frequency or a set of specific frequency. If your signal or your magnetic field happens to be at that frequency, it nullifies your echo protocol, and it creates a very rapid T-coherence. And this is a field which is exactly in sync with your pi pulses. So here you're coherently adding a phase, subtracting a phase, adding a phase, subtracting a phase. But if your signal here is following exactly the same path, you effectively build up a phase and you get very fast T-coherence. So this is either called a multi-spin sequence, a dynamical decoupling sequence, sometimes CPMG sequence, but it's always this scheme where you have many pi pulses. So we use that, and the nice thing is your T2 time. So if you look at here, you have a T2 star decay, which is in the order of a few microseconds. The T2 time you can get here is between 10 and 1,000 microseconds, so you can measure much longer. And the frequency you can achieve is set by the spacing between two pulses, and it's between a couple hundred kilohertz up to megahertz. The other scheme we have used is exactly what I've shown you before with this T1 row. And with the T1, so here a second time with a slightly different picture. If you do a T1 measurement, it's this protocol here. You pump it to the 0 state, you wait a time, you might go back to the 1 state. What you have is an energy level splitting of 3 gigahertz between 0 and 1, and you look at the transition rate between the two levels. If you change this frequency by applying a magnetic field, you can map out the spectral density as a function of frequency. With the T1 row measurement, the appropriate scheme looks like this. With the T1 row measurement, you apply a radio frequency magnetic field that you slowly sweep across a transition. So if you look at the energy levels, they actually move together, and at the closest point, they're as far away as the Rabi frequency. So if we move our spin system to this point and wait here, we detect relaxation, which is now given by not these 3 gigahertz, but by a frequency of our Rabi frequency, which we can tune. And then we can again measure from the time what is the spectral density. Okay, so this is the schemes we used. We used this one here and the one on the previous slide. Let's move on to some examples. So this is a spectrum where we recorded using this T1 row method. So what you see here is a frequency, and here you see a probability of a transition happening between 0 and 1, which is proportional to the spectral density. So what we have in real time, in real frequency space here, is a spectrum of the magnetic noise at the NV center's location. So it's operated as a spectrum analyzer. And what you can see, there's actually a few features. So this feature here we did intentionally. So we recorded the spectrum, and we added a 7.5 megahertz signal from a signal generator with a known magnetic field amplitude. In this case, it was 7.5 megahertz. It was 1.6 microtesla. So you see that the 1.6 microtesla signal shows up in our spectrum analyzer as a sharp peak. There are some more peaks. So we have 1 over F noise, which is caused by C13 nuclei, very slowly either precessing or changing their orientation. We have another feature here, which we are not entirely sure, but it's probably from this N14 nuclear spin, which is part of the NV center. So what we see in the spectrum already is we can distinguish different magnetic fields by their frequency characteristics. Okay, so let me show some improvements on that. We can drive this to the limit and look how far we can go. If we apply the smallest field that we can still detect, it's about 40 nanotesla. And he has a line width of about 10 kilohertz, so this is about 0.1% of the overall spectrum, which is very narrow. And we see with 40 nanotesla, this is less than 100 nanotesla I've shown you before. So we can do a few more tests looking at these C13 nuclei. So we can go to a field from almost 0 Tesla to 220 millitesla. So the precessional frequency of carbon-13 is expected to be at 2.3 megahertz. So if you look at our spectrum, we indeed, at a bit more than 2 megahertz, see a precessional signal from all the C13 spins located around the NV center. And maybe for the record, so carbon has 3 isotopes, 2 stable ones, C12, which is 99%, and C13, which is 1%. So if you have an NV center in diamond, there is stochastically 1 out of every 100 carbons around is a nuclear spin. And those couple to the NV center, and they build up a bath of C13 spins. So we've repeated that experiment with the sample from KO and AIST, which has no C13. And what we see is that this peak disappears, and you have much less low frequency noise. So if you want to have a good sensor, a low noise sensor, you want to remove your C13 spins, and this is exactly what happens with the sample that you guys made. Another interesting feature you can do is you can go back to this one here and zoom in on the region of C13 and record a high resolution spectrum. So this is now with slightly less field, long revolution time, but concentrated on this region around 2 megahertz. And what you can see in this experiment is actually up to, I would say, 8 individual carbons located around the diamond. And they all have different frequencies. Why? Because your electron spin in an NV center is also a magnet. It has a magnetic moment. So by hyperfine, it shifts the frequencies of the nearby carbon-13 spins. So the carbon-13 spins see a magnetic field produced by the NV center. If they're closer, it's stronger. If they're further away, it's weaker. And it can also change sign. So what we have a way is actually here already to map out, in principle, the locations of up to 8 C13 nuclei surrounding the NV center. So we can pull out all these numbers here, like we can count them, get frequencies. From the frequencies, we haven't done it, derive a distance and an orientation. Then how do you know it's single spins? Okay, it's pretty obvious because you have only one and very sharp peak, which indicates it's probably single C13. There's another indication. If you have a coupling to a single spin, you're in principle able to transfer polarization 100%. So a hallmark is if any of the peak here goes above the 50% level, then you basically know it's a quantum coherent coupling. It's not a classical magnetic field you detect. So for this number here, you already see from the height that it's above 0.5, that in principle it must be a single spin. You could also look at the other ones by varying the time, but we haven't done that. So the last thing we did, again, on the sample that you guys made, was to overcoat it with oil in order to try and couple the NV center in here to the protons on the surface. It's just convenient to use oil because we have an oil immersion objective. So there is protons in that oil naturally there. So in this case, you have to zoom into a higher frequency region because the precession frequency of hydrogen is about 4 times higher. So if you record the same spectrum, now focusing on roughly 9 megahertz, you again see a peak. Okay, you see a double peak, which is part of the detection protocol. If you calculate from the magnetic field, which we can calibrate with the NV center, you find that the proton signal should be about here, so almost on the position, maybe 1% off. And then we can also calculate the signal we would expect using the same model as before with many spins on the surface. And you get this line here. You can attribute it a magnetic field, an RMS magnetic field, about 350 nanotesla. And you can also find out how many spins are in a volume that contribute around 80% to that field, which is in this case a bit less than 10,000 nuclei. So we've now tried repeating this with new samples and also different protocols. I think this was by the most successful so far. Mm-hmm. So the key thing to get to this level is actually first to get a good sample which produces very good NVs, very close to the surface with a reasonably long T1 row, and also to have a sample which is just compatible with these measurements. Many of them are fluorescent. We've tried Teflon, for example, which has a lot of fluorine, but Teflon is very fluorescent. So this prevents many of the measurements we would want to do. So one hard point is not only to make the NV center, but also to make the samples, choose them in a way that you can actually use them in the actual setup. Okay, so this was the second part, and the third one is more visual because it's scanning experiment, which show you some images. So I want to show you some first steps and also the instrument that we use to actually integrate this in a scanning probe. So first thing you have to do is you have to, if you want to scan an NV center, you have to somehow bring it to a tip. And this was the first try I made when I was actually still a postdoc working in Leiden in the Netherlands. They have a very nice SEM, so you can make very sharp tungsten tips. So this is a tungsten tip here. Put it in an SEM and move over around on a surface which has not NV centers, nanodiamonds, and purposely pick up nanodiamonds by touching them, and many of them will stick. So there is a way you can use nanodiamonds, stick them to the end of a cantilever or an end of a sharp tip and pick them up. In this case, you could not even pick them up, but also move them around and form this nanodiamond here. So it's a nanodiamond formed from nanodiamonds, and it takes about a day to get there. But, so you see they're still rather big. This is 100 nanometers. But this is a way where you can actually locate nanodiamonds. So we moved on to smaller diamonds and more reliable protocols, and the one we use now is a combined AFM confocal microscope where we can take an AFM image of nanodiamonds and simultaneously record the fluorescence. So we can overlay the fluorescence with the nanodiamond image So from the AFM we see where the diamonds are, from the optical we know there is an NV centers and we can characterize it. You see some here, so these are NV centers here, and you see them up here over here. So then we move in with a AFM cantilever that we chemically modify such that it attracts nanodiamonds, and we push down on a nanodiamond and retract and hope that the NV center or the nanodiamond sticks. This works sometimes it doesn't work that well, but just to show you two examples and maybe to refresh you a little, this is the way we identify them. So we have an image before we pick it up and after we pick it up, and you guys' task is now to find which which nanodiamond is missing. Okay, so some people have seen it. It's the one down here. But it's actually how we verify, and it doesn't go as fast. It's not too slow, but it maybe takes 10, 20 minutes. So here's another example. Okay, it's easier for us because we know where we push down. But, okay, it's this one here. But anyway, this is the way we put them on there. We've done some scanning experiments with those. We've done some more basic experiments just to verify that the scanning is working. And this is by actually not moving an NV center around over a magnetic structure, but having an immobile NV and use a magnetic tip over the NV center to map out the magnetic field of the magnetic structure. And the easiest you can take is a so-called MFM, magnetic force microscopy tip, so a magnetic tip, and move it over the NV center. So what you will record is a drop in fluorescence if you apply a microwave, if the magnetic field produced by this tip exactly matches the field where you apply your microwave pulses. So in this case, I think it was a few corresponding to a few millitesla field, so it was about 100 megahertz above the center frequency of the NV center. So as soon as you move through a contour of field which is roughly 5 millitesla, you see a drop in fluorescence, which is this image to the right here. So you scan over the NV center, it's probably located somewhere here. We don't know exactly where. But we see this ring here, which is a contour of a roughly 5 millitesla field with a, actually no, it's 1 millitesla field, but the line width here is much narrower than 1 millitesla. So what you can see is if you have a low gradient, it's quite wide. If you have a high gradient, it's very narrow. And so 1 pixel is 10 nanometer here. So you can get resolutions down to 10 nanometer or even slightly better. We've improved on that in order to get 3D imaging information. So we have a cantilever. Usually it's oscillating, so we can synchronize our acquisition with the position where the lever is standing. So in principle, we get these 2D slices that you saw before. In a single run, we can get 2D slices according to the height of the lever. So you see here, it's a bit less visible, but you have 9 slices as your cantilever moves up and down, so 1 being closest, 9 being furthest away. And you see your ring being that size here, it actually gets wider, and it forms 2 rings. It forms 2 rings because the NV center has a 1 level, a +1 level, and -1 level. So they show up at different, depending if your field is positive or negative. So we can here record a 7 Gauss line, either -7 or a +7 Gauss line as a function of position. So you record the 2D contour of constant field in a single run. The nice thing is you also get the topography at the same time. So I think it was this nanodiamond here. I don't have the optical image. You also get a fluorescence image, and this is also not shown, but you can record the fluorescence emission or the fluorescence lifetime at the same time. So in principle, in one run, you get topography, 3D magnetic image, and a 3D optical density of states. So I think it's just a nice feature of this instrument that you can get all the information at once. Okay, so the last 2 slides is an overview of the setups we use. We have 2 AFMs. This is a room temperature version we use, which is home built in parts, but then many of the scanning components are commercial. So you have to accommodate a lot of things in a small area. This is a glass slide here, which is about 25 millimeters. So in this case, an objective comes in from below. You see the green laser. On the glass slide, there is the sample. And then from the top, we come with a cantilever. Everything is stationary except for the sample on the glass slide. You can move in 3D. The laser we can scan with mirrors, but it's usually fixed. Then we have the cantilever here, which has either a magnetic tip or a diamond, and we can scan it over the sample. Here we have another thing coming in, which carries a microwave strip line with a microwire to apply microwave pulses. And in this case, we also have a magnet and can coming from the top to apply a magnetic field. So you have quite a few components. You have basically optics, a cantilever, microwaves, and a magnetic tip, and then everything is scannable in the middle. So this is one setup. We have also recently started building up a low temperature magnetometer, which is a bit different. So in this setup here, the laser comes from below, the cantilever from the top. In this setup here, we come with an objective from the top and also with the cantilever from the top. This one is operated in a cryostat, a so-called Montana cryostation. My people dubbed it a Montana coffee maker because it really looks like a coffee maker. Unfortunately, I don't have an image of it, but you could just put a Nescafe sticker on it. It would look perfectly. Yeah. Anyway, maybe you can agree on the coffee maker design, but so it's the nice thing. It's very small and it's closed cycle, so we don't need liquid helium. It has some vibrations, but the levels are so low that with the AFM we can see them, but they're not hurting us. So in this case, we have a chip coming in with a tuning fork. The tuning fork has the image is just reversed. The tuning fork is here, so it is not a microwave chip, but a tuning fork chip. So you see the chip here with a tuning fork, which has a tip at the end. We have another chip here with a microwave strip line, and then the coaxial cables, which have a small wire. And then the sample, which is not, the final stage is not mounted here, but which is coming on from this side, where you can do all the scanning from the top. We have an objective that comes from the top, which has 1 or 2 windows in between if it's in vacuum. Here we have, of course, removed the vacuum to be able to get the whole image aligned. And then it also has an option to come in with a magnet from the bottom to apply a magnetic field. So what do we want to do with it? With this first one, our primary goal is to move towards this magnetic imaging of nano MRI of spins. Here it's more solid state physics, so the low temperature is not for the NV center, but for some structures that people next to our labs are making, which may include nanotube devices or graphene devices, or also magnetically ordered structures that are only stable at low temperature. So this is more a condensed matter apparatus. However, we can also use it to study the NV center as a function of temperature. Okay, so this was I think the last slide. So with the last one, I would like to acknowledge all my people and also the very fruitful collaboration we had with you guys with this sample, and I hope that will continue in the future. And then all the funding agencies where I have to write a lot of progress reports in the next month. So thank you very much for your attention.